A lot of this is repeat of Algebra 2 stuff. Okay, understand, in Algebra 2, we had a whole chapter which is about rational functions. And again, rational means fractions. And in that chapter, because we dealt with expressions and equations, we had to learn how to add, subtract, multiply, divide rational expressions, which was a challenge for us, right? That's not what this is about. We're only doing the functions part. We're only doing the part which is about how do you graph a rational function. And there's like, if there's a difference in here, it's in this last thing right here. Not last, but there's a new kind of asymptote that we did not deal with in Algebra 2. It's called slant asymptote. What we do with these two is virtually the same thing. The horizontal and vertical, that's the same thing. But the slant asymptote, that's a new thing that you probably have not seen before. So first, by rational function, again, we mean a function that could be written as a fraction of polynomials, right? So it's a polynomial in the numerator, a polynomial in the denominator, right? Now, each polynomial by itself, you know, there's no dividing within it. There's no square rooting going on. That would not be a polynomial. The only thing we've got to worry about in terms of domain is you can't divide by 0. So this, whatever the polynomial is in the denominator, cannot equal 0. That is the domain. You know, rational functions don't really have a parent function. Like pretty much most everything we've done up to now, really, you could have a parent function. And then we always talked about how it transforms by adding and subtracting numbers and putting minus signs in front. We don't do that with rational functions because their graphs are just too dissimilar. Their graphs are characterized by asymptotes, by vertical asymptotes, by horizontal asymptotes, by slant asymptotes. That's what we spend most of our time dealing with here. Yeah, I'm going to, some of these slides here, it's going to be just something from the textbook that I've copied and put in here. Please do not try to copy them all. Just look in your book, right? You got that thing. It's right there. Just say, see book, something like that. We don't want to sit here all day copying things, but you actually already have a copy of. Okay, we good? Good. In fact, when I say there's like not one parent function, this one is kind of like, of all the rational functions, there is one that kind of gets that label of being a parent function. In our book, when we did that section on the common functions or parent functions, it was in chapter 1, they called 1 over x the reciprocal function. But we learned it in Algebra 2 as an inverse variation when you're dividing by x. And it's a graph that has one branch in the first quadrant and one branch in the third quadrant. Okay. Because of the function, I mean, we know by now that to find the domain of that function, I would be looking for the values of x that led to a divide by 0. In this case, it would be 1 over x, the domain is. X does not equal 0, right? X does not equal 0. Okay, which means on your graph, you have a horizontal or vertical asymptote at x equals 0. Right? These branches of the graph are going to, can never touch that line. Right? That's what a vertical asymptote is. But also, just by the nature of the function there, 1 over x. Remember, if a fraction equals 0, that means the numerator equals 0. But the numerator is a constant. It's 1. I mean, this thing can never equal 0. There's nothing you can plug in for x that would make 1 over x equal 0, which means it has a horizontal asymptote here. So x equals 0 is vertical asymptote. Y equals 0, horizontal asymptote. Okay. Now, the thing to notice, when a graph approaches a vertical asymptote, what does it do? It veers off towards either negative infinity or positive infinity, right? As it gets really close. I mean, in this fraction, if the graph is approaching the vertical asymptote at x equals 0, that means the x value is becoming really, really, really close to 0. And what happens to the value of the function when you're dividing by a number which is almost infinitely small? Well, the graph, the whole fraction goes infinitely large, right? So the graph, when you approach a vertical asymptote, is going to veer off towards infinity or towards negative infinity. Right? As x approaches the vertical asymptote, y approaches positive or negative infinity. Good, Jimmy, Courtney, Ariana, you good? And I'm just going to throw this one up just to show, but notice the difference between the graph of 1 over x and the graph of 1 over x squared. They still have to have a vertical asymptote here, right? And still going to have a horizontal asymptote here, right? But notice that now both of the branches are first and second quadrant. It moves this branch here. Why? Because you're squaring it, it's always going to be positive, right? But it's the same kind of thing like when we see zeros, right? A 0 on a graph, we know that when it comes from a factor which is raised to an odd power, then the graph goes right through the 0 to the other side because it changes sign, right? And then this is what it looks like when the factor is squared. It has a multiplicity that's even, right? It stays on the same side. Well, that's what's happening here. If you ever have like the vertical asymptote is coming from a factor which is raised to an even power, then you would expect that it's approaching, the asymptote from both sides and going to positive infinity on both of them. I've seen that come up on some tests. I don't know if it's like a test that it's not a test I made up. It might be an Algebra 2 SOL thing that I saw that at. Okay. So this is an example of one of these graphics, okay, that you don't have to copy every little piece of this. There is a difference between a vertical asymptote and a horizontal asymptote, okay? A vertical asymptote is a vertical line that the graph of the function absolutely will not touch, okay? Vertical asymptotes are absolute, hands-off, you're never going to touch it, right? The graph can come up to it and just veer off towards infinity or something like that, but it will not ever get to that line. A horizontal asymptote is not the same thing. The horizontal asymptote, I could have a horizontal asymptote at y equals 0, right, and still have a graph that, let's say I've got 3 pieces to the graph. I could have a graph that looks something like this. There's one branch, there's another branch, and there's the last. But notice that in the middle of the graph, it crosses the horizontal asymptote, right? The horizontal asymptote is really describing the end behavior of the graph. What's the graph doing when x approaches infinity or negative infinity? Out here, not in the middle. So you will cross horizontal asymptotes. Actually, you'll cross the slant asymptotes when we get to those too. But a vertical asymptote, you never cross. Absolutely never cross. So that's what I would take out of this thing as far as what are the definitions of vertical and horizontal asymptotes. You know, this is hands off. This one, for small values of x, you'll cross it sometimes. So here's all of our rules for finding those asymptotes. If you have a rational function, right? It's a polynomial in the numerator, a polynomial in the denominator, right? Each one has a degree, right, which is the highest power of x. In the way that it's written here, they've got the degree of the n, the numerator is n, and the degree of the denominator is m. Okay? So those will become important when we do the horizontal asymptotes. Okay, the vertical asymptotes are the zeros of the denominator. Makes sense, right? Whatever value you would plug into dx to make dx equal to 0, those are the zeros. That would be where you find the vertical asymptotes. Right? It's like the domain would be x does not equal this number. The vertical asymptote would be x equals that number. Right? That's how you find those. There's for the horizontal asymptotes, there's 3 rules, right? And it depends on the n and the m. Okay. If the degree of the numerator is less than the degree of the denominator, that's this one right here, then the horizontal asymptote is y equals 0. Right? Always y equals 0. Just like the f of x equals 1 over x that we just did, right? Which has a higher degree, the numerator or denominator? Denominator, it's x to the first. Numerator is a constant. So that would have to have a horizontal asymptote at y equals 0. And it did, right? We already saw that. Okay. If, I'm going a little out of order, if the numerator has a higher power than the denominator, that's this one, there is no horizontal asymptote, right? That would be that. And last, what if they're equal, right? If the n equals m, and these two are actually the same power, then it's y equals the ratio of those numbers. Right, those are the 3 rules that we apply. So the vertical asymptotes, zeros of the denominator. Horizontal asymptotes, apply the right rule. The whole problem. So for example, in this one, how do we find the vertical asymptotes? Zeros of the denominator, right? So I'm going to abbreviate here. Vertical asymptote. So it's the zeros of the denominator, so set the denominator equal to 0 and solve. Find those values. Right. This is a factorable problem. X plus 3, x plus 1. So the zeros are x equals -3 and x equals -1. Those are the vertical asymptotes, the zeros of the denominator. Okay. The horizontal asymptote, right, in terms of that definition we got on the last page, you know, if the numerator was n and the denominator was m, which situation are we in right now? Is n bigger than m, or they're equal, right? This is the situation where n equals m. They have the same degree. So what does the rule say? It should be the ratio of the coefficients of the highest degree terms. Y equals 3 over 1, or y equals 3. Done. Right, so horizontal or vertical, 0 is the denominator. Horizontal, apply the 3 rules. Okay. The zeros of the denominator. I set the denominator equal to 0, I solved. Okay. That's skipped. Okay, same problem. I just changed it by one thing. So note the denominator is the same. But what's the new horizontal asymptote in this problem? Okay, now we're the situation is the n bigger than m, smaller than m, same as m? This is the n is bigger than m situation, right? And by the rule, that tells you what? There's no horizontal asymptote. The one thing to watch out on these, when you want to apply these rules, it has to be a rational function. If it's like written as multiple terms being added together and that, okay, that's not a rational function. A rational function is a numerator over a denominator. Okay, good, good. Now, how about this one? Horizontal asymptote only. Yeah. For the horizontal asymptote, right? This is the n is less than m situation. And when n is less than m, right, 1 is less than 2, y equals 0. Right? If you have to say what a horizontal or vertical asymptote is, you got to make sure you say y equals or x equals. The number by itself is not going to get you credit because that's not a line. And because a lot of you actually are confused about vertical and horizontal lines, you actually could be exactly the mean exactly the opposite. So definitely say horizontal is going to be a y equals, right? Vertical is going to be an x equals. Don't just say 0. 0 is not an asymptote. Okay, again, another thing not to copy the whole thing of. But most of what we do now is just sketch some graphs, right? And I'm going to sketch, I'm probably going to do like 2 of them. There's 4 in there. I'm going to do 2 of them in this class, and then I'll record the other 2, and I'll make sure they're all online if you want to look at them. But there's some basic steps here. The first step, when they say simplify f, I'm not really sure what they mean by that. It could be that it's not a rational function, so you got to like do something to make it a rational function so that you can apply the rules, right? The second step is find the y-intercept. Okay, how do you find a y-intercept? You plug in x equals 0, right? The second step will be find the zeros of the numerator, because the zeros of the numerator will be the zeros of the function, right? So let's see, the zeros of the numerator, and these are zeros of the numerator are the x-intercepts. They're the zeros of the function. Okay, find the zeros of the denominator, because what do they tell us again? The zeros of the denominator are vertical asymptotes. Okay, find and sketch the horizontal asymptote using our rules. Okay, and this is the part, we did a little bit of graph sketching of polynomial graphs before, but this is the part where it says, okay, now fill in a few points, you know, in between all the things that you already put on the graph, fill in 1 point in between all the significant x values, 1 point beyond, sketch a curve. Right, so let's do a couple. But first, before we do one, there's a lot of this stuff that we do that actually the calculator has kind of overcome our need to do this. But sometimes rational functions, if you try to graph them in the calculator, you get graphs that look like this, which are not accurate. Because it has a real hard time with vertical asymptotes. It could either do this kind of thing where it just kind of like the graph disappears, or it could do this kind of thing where it connects like this branch and this branch with a line that's actually not there either. Right? So our sketching of the graphs will probably come up with a little better graphs than the calculators sometimes. And I'm not sure if there's like some variety of Texas Instruments calculator that does better with this, but most of the ones I've seen, even the 84s, do have this problem here. Okay, so let's go down our list of things that we're going to do. The first thing, there's no simplifying to be done at this one. What was the first thing in that list? It was y-intercept. Okay, the y-intercept is, right? The y-intercept is what you get when you substitute x equals 0. Right, so y equals 1 over 0 plus 3, 1/3. So 1/3. Oh, that's wrong. Edit, undo. 1/3. Okay, the next step was find the zeros, right? The zeros of the numerator will be the x-intercepts. Okay, x-intercepts. Okay, does this thing have any zeros of the numerator? It's a constant, so there's none. Okay, vertical asymptotes. Well, how do you find the vertical asymptotes? The zeros of the denominator. Okay, what's the zero of the denominator? X equals -3, right? So let me sketch that one in there. That is a line. I'm going to make it red. I'm going to make it dashed. And that's probably good. X equals -3. That's good, right? The horizontal. Okay, which is a higher degree, the numerator or the denominator? Denominator has a higher degree, so that the horizontal asymptote is y equals 0. So sketch that on there. Where are we at? And last, plot a few points. The significant values that we've got are only this vertical asymptote and the y-intercepts. There's really nothing else there. So maybe we could sketch a couple points over here. Let's see, in the table of values, I'm gonna look for these points, x, y. How about I'm gonna kick. Well, I'll just do exactly what it says, right? It says take 1 point beyond the leftmost. So let's pick 1 point over here. How about 1, 2, 3, 4, -4. And pick 1 point in between these two. How about -1? And I'll pick 1 point beyond it. How about 2? So I'll put into the function. 1 over -4 plus 3 would be -1. -1 plus 3 is 2, so that's 1/2. And 1 over 2 plus 3 is 1/5. So let's plot those points. -4, -1. -1, 1/2. And 2, 1/5. Again, now understanding that what is the graph going to do as it approaches the vertical asymptote? It's going to be veering off towards infinity, right? So we know that this graph, we could see these points that where they're going. So let's just go like this. And then the other branch should be in this quadrant. Tricky? You see the pattern, it's y-intercepts, x-intercepts, vertical asymptotes, horizontal asymptotes. Plot a few points, sketch your curve. You ready for another? Give me more. Okay, here's our function. 3 plus 2x over 1 plus x. So first step is y-intercept. Right, that'll be what do we get when we substitute x equals 0. 3. Right? If you substitute x equals 0, that term is 0, that term is 0. So we just get 3. X-intercepts. Okay, remember, how do you find the x-intercepts? Zeros of the numerator. So set 3 plus 2x equals 0. That is going to give x equals negative 3/2. Okay, vertical asymptotes. How do we do the vertical asymptotes? Zeros of the denominator. Okay, what are the zeros of this denominator? What's that? Negative 1, right? It has nothing to do with this. Negative 1. So vertical asymptote, x equals negative 1. Horizontal asymptote. What's going to be the horizontal asymptote? I mean, what the degree of the numerator and denominator are equal, right? So it's going to be y equals 2 over 1, right? Don't look at the 3 over 1 because that's not the highest degree term. Look at the 2 over 1. So that'll be y equals 2. So let's sketch those in. It's red and double. X equals negative 1 is here. And y equals 2 is here. Sketch the graph. Oh, no, we're not ready to do that yet. Now we've got to fill in a few points. Okay, let's see. You know, the difference between that point and that is so close, I'm not going to pick a point in between them. But let's pick a point that's over here somewhere. How about 1, 2, 3, 4? How about negative 4? It's probably going to be doing this kind of thing anyway, so negative 4. Okay, and then, again, I think like in between these two, I don't particularly want to do that. How about we'll pick one over here? How about 2? And let's just leave it at that. Okay, when you put in a negative 4, that'll be 3 minus 8, which is negative 5. And 1 plus negative 4 is negative 3. Negative 5 over negative 3 is 5/3, I believe. So negative 4, 5/3 is almost 2. It's about right there. And at 2, that'll be 3 plus 2x to be 7 over 3. About a little more than 2, 7/3. Okay, and then what do we expect are doing as they approach the vertical asymptote? They're going to veer off towards infinity or not, right? And as x becomes really large, right, it's going to approach the horizontal asymptote. So sketch the graph. good. Yeah, I'm going to do this one more before we do the next thing. Okay, so let's see. 3x, I'm going to write it like this. 3x over x squared plus x minus 2. But that denominator, I know I'm going to end up factoring it. So what's going to be the factoring of the denominator? Yeah, it'd be x plus 2, x minus 1. So in that form, everything will come out a little easier. Okay, first the y-intercept. Right, what do you get if you substitute x equals 0? Here, here, and here. 0, because the numerator is 0, the whole thing's 0. Okay, the x-intercepts. The zeros of the numerator. 0, right? 0. Which makes sense because it's a point 0, 0. It's got to be both an x and a y-intercept. Okay, the vertical asymptotes. The zeros of the denominator. X equals negative 2, x equals 1. And what's the horizontal asymptote? The horizontal asymptote, it's the higher power is in the denominator, so y equals 0. So let's put those on. X equals negative 2, x equals 1, and y equals 0. Okay, go back to this. Now we need to fill in a few points. So we need something to the left of this asymptote. How about at negative 3? We've got this point there. How about we'll put at negative 1? We'll see, is it doing this kind of thing or is it doing the opposite kind of thing? Negative 1. And then we need to pick a point over here. Let's pick 2. Right, if we do the negative 3 is going to give us negative 9 over 9 minus 3 minus 2 is 4. Negative 9 over 4. Negative 2 and a fourth. Which would be about there, if I did it right. You can correct me if I'm wrong there. Negative 1. Negative 3 over 1 minus 1, negative 2. Negative 3 over negative 2, 3 halves. That looks good. And the last one, 2. 6 over 4 plus 2 is 6 minus is 4. 6 over 4, 3 halves. Two, 3 halves. Okay, so those are our points. And we can sketch in a graph. Right? We expect that the graph is doing this and this. Right? You could see the shape of it here, so I have a hard time seeing that. And like this. Okay, so notice this thing here. The graph crossed the horizontal asymptote. Remember, that's okay, because x is small. X is right around 0, right? The horizontal asymptote is what the graph approaches when x becomes large. It won't cross it over here, but it can cross it when x is small. And the last one, I'm not going to do the whole one. I'll do it later. Okay, there may be a little bit of a disconnect in the playback of the video because I had to come back and do over the last few problems. because I knew I was not going to get to everything in class anyways. But I'm going to just go ahead and go back to this example, which I think it's about example 6 or something like that in the book, maybe example 8. You can find it anyways. But I do want to show it. So if anybody's going back to look at the videos, you've seen everything at this time. So sketch the graph of this function. And again, if I write this function, because it looks easier to see, like this, right? X squared minus 4 over x squared minus x minus 6, and then factor the numerator and factor the denominator. What we'll see here is that this is different than the other problems that we've done up till now, because this time one of the factors in the denominator is shared with a factor in the numerator. And we know we use the zeros of the denominator become our vertical asymptotes. But when you can cancel a factor in the denominator with a factor in the numerator, it's going to make the graph behave like just what's left, x minus 2 over x minus 3. Except for one exception, which I'll throw in right at the very end. Okay, so having done all of that, now we'll come over and follow our steps, right? The guidelines for sketching a rational function. First thing, y-intercept. Okay, so if I substitute a 0 for x here and here, then I get negative 2 over negative 3, which is 2/3. Right? That is f of 0. So 2/3 will be about right there. The x-intercepts will be the zeros of the numerator. Well, the only 0 that's left in this numerator is 2, so I'll put that there. The vertical asymptotes are the zeros of the denominator, right? And it's a vertical line, so I have to say it like x equals 3, right? The horizontal asymptote, given the fact that it's x to the first over x to the first, they have the same degree, so it'll be the ratio of the coefficients, which is y equals 1. Okay, now I can put all of that on the graph. Let me put in our asymptotes. The asymptotes I'm putting in as a dashed line in red and double thick, right? So let's see, we said x equals 3, that would be right here. And y equals 1, that would be right here. Okay, and with all that on the graph, let's go ahead and make our table of values and pick a few more points that will help us to see what's going on here. I'm going to do it up here. Remember, the guidelines tell us that we should be picking points in between and points beyond. Basically, pick enough points so you can see what's going on with the shape. Okay, so I mean, at this point, I can be pretty sure that there's going to be one branch which is approaching the vertical asymptote off towards negative infinity. I'm not quite sure what's going to happen here. It's possible it's going to approach, the graph will approach the horizontal asymptote when x is large, but we don't really know what's going to happen in the middle of this function. So let's pick a value that's over here, like negative 4, and see whether it puts us above the line or below the line. All right, how about negative 4? And I think I can see with that I'll be able to sketch in the rest of this graph. And then let's pick a value in here. You know, tell us whether it's above or below the line. Anyways, let's pick 2. Let's pick 4 and 6. And again, for my table of values, I can use this simplified function x minus 2 over x minus 3. So negative 4 is going to give me negative 6 over negative 7, which is 6/7. which at -4, positive 6/7 is a little bit more, a little bit less than 1. So it looks like it's coming up from the underside. Do I have this all wrong? See, there's the intercept. I said no, it's at 3. Oh, I'm sorry. Yeah, I'm part of this. It should be right there. Right, that was a mistake. The only mistake there was just I was putting that where it didn't belong. Okay. So this is better. 6/7. Okay, let's put in 4. 4 minus 2 over 4 minus 3. 2 over 1, which is 2. So at 4, we are at 2. And how about 6? 6 minus 2 over 6 minus 3. That's 4 over 3, 4/3. So I think we can see what's going on there, right? So let's sketch in this graph. Looks like there's one branch, which is here. And there's one branch, which is here. Okay, but there's one difference now that we've got to put in there because of the fact that we actually divided out one of the zeros of our denominator. That 0 was at -2. That means at -2, we should go up to the graph and there should be a hole, right? And I can put that in there just a little more clearly, like this. There we go. So the graph is, it's not like a vertical asymptote, right? It's not going off towards infinity. It's just jumping over that one y value when x equals -2. So that's what it looks like if you have a factor in the denominator which cancels with a factor in the numerator. That's called a hole, right? If you did this in Algebra 2, you might have called the holes and vertical asymptotes together were called points of discontinuity. Okay, and I never did write this in here. So let's write this in. 6, it was 4/3. Okay, so there's a graph. Okay, now there's one more concept that gets added in here, and that is slant asymptote, right? A slant asymptote is kind of like a horizontal asymptote, at least what it does for us. But it's not horizontal and it's not vertical, it's slanted, it's tilted, right? It has a slope which is not 0 and it's not undefined. It's in there. So when you get a slant asymptote when the degree of the numerator is exactly 1 more than the degree of the denominator. So if you see in this problem right here, x squared in the numerator, x to the first in the denominator, clearly there's no horizontal asymptote because of that, but there is going to be a slant asymptote. Okay, so slant asymptote, right, is only for the case when the degree of the numerator is 1 more than the degree of the denominator. Okay, and the way you find the slant asymptote, you do long division. Divide the numerator by the denominator. So let me do this. I will go x squared minus x divided by x plus 1 and go through the long division. That'll be x times x is x squared. X times 1 is x. Subtract, that's negative 2x. Okay, we don't have a constant term. I'll write in a 0. X times negative 2 is negative 2x. And then negative 2 times 1 is minus 2. So I subtract, and I get, that was a sloppy move. Subtract, and I get positive 2. So this fraction equals x minus 2 plus 2 over x plus 1, right? That's the remainder divided by the divisor. Okay, now, we're interested in this, like I said, more like a horizontal asymptote than a vertical asymptote. This is going to be a line that the graph approaches when x becomes really large. It's not like a vertical asymptote that the graph can never cross, right? It can cross when x is not very large. But if x were very large, right, if what would happen to this term as x approaches positive or negative infinity? Well, the denominator would become almost infinity, and the whole fraction would become 0, and it would drop out. So the only thing that's left is the first part of this, which is y equals x minus 2. And that is a straight line. Y-intercept is -2, slope is 1, sketch in a line, that's a slant asymptote. Okay. Once you've determined that you've got it, it just becomes another step in the process of graphing. Right? When you check for the asymptotes, check for all of them. Right, so here will be an example. We will graph it, and clearly there's going to be a slant asymptote. So let me rewrite this first. Let me call this x minus 2 times x plus 1 divided by x minus 1. Okay, just factoring it because it'll make certain parts of this problem easier if I do that. And let me do this because I meant to have deleted these guys before I started this. Don't want to ruin the mystery of this problem. Okay, let's get back to this. Okay, so first, y-intercept. Right, the y-intercept you get when you substitute x equals 0. Right, so in this problem here, if this term is 0, and this term is 0, and this term is 0, then y equals -2 over -1. 2. Okay, the x-intercepts are the zeros of the numerator. Okay, well, in factored form, you could see the zeros of the numerator are 2 and -1. So I can plot those, 2 and -1. The vertical asymptotes are the zeros of the denominator, and with a denominator of x minus 1, then the 0 is x equals 1. Right, it's a vertical line. The horizontal asymptote, well, since the numerator has a higher degree than the denominator, there is none. But we notice the numerator is exactly 1 higher power than the denominator. So we need to find the slant asymptote. So we do that by doing long division. X squared minus x minus 2 divided by x minus 1. Okay, x gives us x squared minus x. Subtract. And what's left is, I mean, they're both are 0 here. So I bring down the -2, which just becomes a remainder. So this is going to be plus -2 over x minus 1. Okay, so this part of it, when x becomes large, will go to 0. So we can forget about that. And this part of it is the slant asymptote, y equals x. Slant asymptote, y equals x. So let's put all that stuff on the graph, or all the asymptotes anyways. Vertical asymptote at x equals 1, that'll be right here. The slant asymptote at y equals x, right? That is a y-intercept of 0 and a slope of 1. Okay. And now we make our table of values. We shouldn't need too many points here. We can kind of see, it looks like there's going to be one branch in here. There's going to be one branch in here. Let's graph a point which is out here somewhere. How about 1, 2, 3? How about -3? And then let's pick a point that's out here somewhere. How about 3? Maybe it'll make it somewhat easier. Okay, so if I plug in -3 here, I get 9 minus -3 is 12, minus 2 is 10. 10 over -4, which is -2.5. If you're not sure, put it in the calculator, check my math. Right, that's about right there. And +3, 9 squared minus 3 minus 2. 3 squared minus 3 minus 2, which would be 9 minus 3 minus 2, which is 4. 4 over 3 minus 1. 4 over 2, 2. And I think those 2 points just confirm what we kind of already suspected in terms of the shape of this graph. It looks like it'll go something like this. Right? Remember, as it approaches the vertical asymptote, it's got to veer off towards positive or negative infinity. And that is the graph. Okay, word problem. The cost, C, in millions of dollars of removing P% of the industrial and municipal pollutants discharged into a river is given by, and we have a, got to get the calculator opened up. We have a rational equation, a rational function. Find the cost of removing 20%, 45%, 80% of the pollutants. Well, let's see. I think in the homework problems that are similar, and there are 2, that you might be asked to graph with your calculator. So I'm going to add that step to it right now. It might actually help us solve the problem too. So in the calculator, here we go. So y equals clear, clear. So if I have to graph this in the calculator, first I can see the domain is supposed to be from 0 to 100. Right? That's going to be important when I set the window right here. Right? I'm going to want to set my window to go from 0 to 100 in the x values, because p is the independent variable just like x. So let me set this 0 to 100. Okay, and I'll let the scale be every 10. All right. The thing about, we need to figure out how high we should go in the y direction. You can see, we can never, when we get to the right side of our window, 100, that value is actually not defined in this, right? Because if you plugged in 100, 100 minus 100, you'd be dividing by 0. So we need to have some other way to estimate, you know, how high should we draw our graph. And what I usually have done is just, let's put in 99 then, okay? Or just an estimate. I mean, if I did 100 on the top, I'd have 25,500, but I can't use 100 in the bottom. Maybe I'll just use 99. I'm going to guesstimate that if I use 30,000, that'll be okay. So let me just go with my y values and put in a nice round number there, like 30,000. And I'll make my tick marks every 5,000. All right, now let's go over to the function. Let's put it in the calculator. 255 x divided by parentheses 100 minus x. And now let's look at our graph. We should get a graph that looks like it's, you know, these are very small values until it gets to about here, and then it veers off towards positive infinity. So what does that look like? How about a vertical asymptote? Okay, now we want to find the cost of removing 20, 45, and 80%. So you could plug in one at a time, 20, 40, 5, and 80. But since I already have it in the calculator, I'm going to let the calculator do that. Let me set my table set to the independent variable, meaning the x, to ask. And then when I go to my table of values, I can just put in 20, 45, and 80%. And those are the three values that you would put in. I mean, I could even be tricky about it and say, all right, that's our letter A. Hard to see? Blow it up. So there's A. Second, according to the model, would it be possible to remove 100% of the pollutants? Meaning, can we plug in P is 100? And your answer would be no. That would be a divide by 0. P is 100 is a vertical asymptote for this graph. So the answer for B is no. In the real world, practically speaking, what this means is you're never going to get rid of 100%, right? Or the cost of doing so is prohibitive. You just, at a certain point, you're going to say 80% is good enough, something like that. So you have two problems like this in the homework. One's an even, one's an odd. So the odd one you could check. The other one, like I said, I think you're going to have to actually graph it, not just calculate the values and answer a question. And I think that was the end. So I'm going to try to append this to the other video that I made in second block today. Right, that is the homework, and that is the end.